Project Division. We started way back when Hubble needed to be serviced. It was designed for servicing, right? So when Hubble went up, you guys may be familiar, it had some optics trouble. So our group is the one that went up there and fixed all that up. Soon after that, we moved on to robotic servicing, and we did a number of technology demonstrations, one of which was robotic refueling mission, which was up on space station, and it demonstrated how the robots could refuel on orbit robotically. These are some examples of the different fuel interfaces that we have, and I don't know anything about that because I'm a laser guy, so I'll get to that in a second. But so robotic refueling mission. Another demonstration we had is called Raven, which is a demonstration of the autonomous rendezvous and docking sensors and algorithms that we use to fly up to non-cooperative spacecraft, meaning a spacecraft that wasn't designed to be refueled. There's a model of it back there if you guys want to take a look at it. It's a sensor package that's an IR camera to sense heat, optical camera, and a LiDAR. LiDAR is what I worked on. The LiDAR that we flew there is a 3D LiDAR. It's a flash LiDAR. The whole point of the LiDAR is to generate a 3D point cloud and extract three-dimensional information from the scene so that machine vision algorithms can process that and estimate the relative attitude and position of the client spacecraft. Behind me is a full-scale mock-up of a client spacecraft. It's the Landsat 7. Missing a giant solar array, but that's the main bus. On the bottom, the silver thing is what the front of our spacecraft called Restore would look like. Restore is a technology demonstration. This will be the first time that NASA or any other group has flown a spacecraft up to another spacecraft autonomously, meaning it's like a self-driving car in space, so it doesn't get much cooler than that. We're gonna fly up to the spacecraft. We gotta get the end of the robotic arm in a volume the size of a beach ball and hold there about 1.5 meters away from the other spacecraft. And then the robotic arm will automatically reach out and grab a metal ring called the Marmon ring, which is what the spacecraft interfaces the launch vehicle with. Once the robotic arm grabs onto it, it'll close the distance between the two, and the berthing posts, which are the 3 metal posts sticking up from the ground there, will lock onto the Marmon ring. And at that point, we can start to do teleoperated refueling. So that's kind of pie in the sky. That's the goal. That's what we're working to now. Like I said, I'm the LiDAR guy. I work on the machine vision algorithms and the sensors. For Restore, we're going to fly a scanning LiDAR, one that we actually built here in-house at Goddard. It is a MEMS scanning LiDAR. It's based on a MEMS mirror. It steers a laser beam around. And I have a video here I can show you how it works. But I encourage you guys to ask a lot of questions because I told you I'm not a good tour guide. So. Talk about the laser real quick. I guess this is about laser, right? So we, in the flash LiDAR, we have a passive Q switch laser, which means it's an analog laser. It has a lot of it's high power, high peak power. It runs about 30 hertz. For Grizzly, which is our scanning LiDAR, it's the Goddard reconfigurable solid state scanning LiDAR. We have a fiber laser, which is actually a derivative of the LCRD laser, which maybe you guys have already heard about. If you haven't, then you will. That fires about 200 kilohertz. It's about half a watt optical power. It's 1550 nanometers, which is a shortwave IR. I mean, you can't see it, and it's actually the eye-safest version of the laser that you can have. So what does that actually do? I'm sure you guys can't all see this, but so at the beginning of this video, it shows you what Raven sees on the space station. It's looking at the Cygnus vehicle. It's a resupply vehicle for the space station. Like I said, the ramp has a number of sensors, one of them optical. We have a pan-tilt unit for tracking different spacecraft. That was the optical camera and give you a sense of what we're looking at. These are some range images using the flash lidar, where color represents range. The flash lidar actually generates intensity and range imagery. And then this video is a demonstration that we did actually 2 weeks ago, showing that we could use the scanning lidar, Grizzly, to take a picture of a full-scale aft bulkhead model, which is basically the bottom end of the gold spacecraft, right? So that's what we would track when we're rendezvousing with the spacecraft. We made the relative attitude and position of the target spacecraft, so the computers know where you are, where the other guy is, how far you need to go, and if you're too close or not. So, what else we got? Anybody have any questions? Yeah, absolutely. We work pretty closely with the human exploration folks down at Johnson, and we do it. They tag along for all of our testing that we've done. We can use this for cooperative rendezvous and docking. The big distinction here is that this spacecraft that we're flying up to is not designed to be rendezvous with, right? There's no retroreflectors on there. There's no special features to track optically. So every rendezvous they do in the space station is a cooperative rendezvous, right? They try to make it as easy as possible, so they don't screw it up, right? So with us, we're trying to show that we can fly up to anything, non-cooperative. We can grab onto it and dock with it and service it. We can either refuel it or say the solar array didn't deploy. We can take the arm and push the solar array out and potentially make a junk spacecraft usable again. So as a technology demonstration, we're here to prove that it can be done, and companies are already interested in adopting this technology to service their fleets of comsats, for example. Right? Instead of when a communication satellite runs out of fuel, instead of just sending it to the junk heap and flying another billion-dollar spacecraft, you have another guy up in orbit that can come just get more gas and extend a usable life. Yeah, so the resolution on these images, in that range imagery, is about 6 millimeters. The frame rate on that, for those scans, about 3 hertz. We're doing 65,000 pixels or so. So since it's a scanner and some MEMS mirror, we can point however we want, right? So if we fire the laser every 5 microseconds. So we've done, 128 pixels square. You can do 12 hertz images, so it's more, it's higher frame rate. So you can track things that are moving faster. If it's not moving very fast, and you want more resolution, you can scan it slower. The system's actually capable of 16 megapixel, so you can sit there and stare like you're on a rover. You could scan a rock in really high res. Yeah, but I mean the space debris, in theory, would probably be moving a little bit faster, right? So you probably need a higher frame rate. Yeah, these are the refueling attachments that you might see when you're servicing a spacecraft. We have with robotic arms. There's a whole toolbox of different types of tools, right? And so when you go up to service on the spacecraft has been sealed up, right? Nobody expected anybody to go up there, right? So you have to have tools for cutting the blankets away, cutting these wires that have caps in there. There's usually 3 different caps in there you can unscrew and remove, and you need a different tool for doing every single one of those things. So they do a lot of testing here with these robots and the different attachments and cameras and algorithms and operations, and so you practice over and over and over again. Yeah, I mean you need to know what you're going up to, right? You need to be able to practice with it. But you know, the cool thing about the servicer is that since we can rendezvous with things, we can rendezvous with another tool belt. Yeah, so we could get more fuel for ourselves and for another client, change our inclination or our altitude, and go and service another spacecraft. The mass? The mass of the LiDAR, it's on the order of 10 kilograms. It's a couple different boxes, of main electronics box and a front-end box. About 40-degree field of view. The one that we're building for Restore actually has two front ends. It has a telescope for long range, for ranging up to about 1 kilometer or so. And then it has a wide field of view for the pose acquisition and tracking up to the capture box where we actually grab on. And the range for that is on the order of about 40 to 50 meters or so. Yeah, there's only one Raven. That's the one up there right now, operating, making these types of videos. There's talks on building another one with next-gen sensors, next-gen computer software and hardware. A big part of Raven was demonstrating that the machine vision algorithms that we run on these cameras can actually sit on a flight processor that can survive the space environment and collect the imagery in real time and process a solution and generate that in real time. So it's more than just pointing and taking pictures. It's the software and FPGA firmware that actually process those images in real time. So that was a big effort. And a lot of that's just going to be reused on Restore. Yeah, the range is a signal noise ratio problem, right? It's kind of just like radar, right? Say you have a candle in the daytime, right, like 100 meters away, you may not really be able to see it, but if it's dark out, the noise environment's suppressed and you can see it farther. So it's all determined by a balance of a whole bunch of factors that determine like aperture size, field of view, the amount of power in your laser, the amount of sensitivity in your receiver, how reflective your target is, so how much energy you get back. You can imagine if you shoot at this really reflective MLI and you have multi-layer insulation, you gold stuff on it. If you're at the right angle, you're going to get a whole bunch of it back, so you're going to get a really bright reflection. That's if you're at a good angle. If you're at a bad angle, all your laser energy is going to fly off into space. You're not going to get anything back. Also, with a really dark asteroid, for example, we were working on the asteroid retrieval mission. The reflectivity that we were assuming there was 6%, so we needed to juice up our laser quite a bit to get that 50 meters of range that we wanted. We were considering changing the wavelength to a 1 micron, which you can get more sensitive detectors at that wavelength. But right now we're using the iSafe wavelength because we have a requirement to work with Orion and have the technology that we develop on Restore be easily transitionable over to that manned space flight. And when there's people involved, they care about iSafe. Raven's not an acronym. Yeah. Good question, though. There's a lot. Yeah. So Grizzly's the LiDAR, well, it's the LiDAR technology development that we did. For Restore, we're going to fly it. The LiDAR is called Kodiak, which is not an acronym. So Raven is a bunch of sensors and computers, right? Kodiak and Grizzly are versions of a LiDAR that could be integrated into a different version of Raven, right? So Raven, sorry if I wasn't clear. So Raven is the technology demonstration of the rendezvous and proximity operations sensors and algorithms and ISS, right? So Raven is a portion of the technology that would eventually be integrated into Restore, just like robotic refueling is a portion of the technology integrated into Restore, right? Where robotic refueling is the arms and tools and procedures and how they do that teleoperating, right? And then Raven is the real-time algorithms, the sensors, and showing that we can track the incoming spacecraft, accurately estimate the relative attitude and position. So while I got you here, this test that they're setting up for is going to be pretty cool. But, I don't know all the details, but basically we're going to take an aft bulkhead models, basically the aft end of that guy, which is what we have in the corner, and put it on a robot and it can actually simulate zero-G, right? And so we'll have a robot much like this one, or maybe actually this one, I'm not sure. And that robot will have the system set up to, if the robot bumps the spacecraft, then it will actually float away like it would when you're in space, right? So we're going to use that setup to test algorithms and procedures for autonomous grapple. It's an autonomous grapple test. And so for that test, once we get kind of good at it, we're going to have the RPO sensors, rendezvous proximity sensors, like the LiDAR and the cameras, telling the robot where it actually is in space relative to the floating spacecraft, right? So through that test setup, we're going to be able to test the real scary part of the mission over and over and over again, right? And that's basically what we do here, right? We build the stuff, we do our best with the time that we have to analyze things to death, right? But at the end of the day, unless you can actually do it and convince yourself that you know what you're doing and try to break it and it still works and do it over and over again, and that's how you prove that you're ready for flying.
Does that display one of those edge view of Raven?
That's a good question. I mean, those are real-time feeds from ISS.
Yeah.
Not sure what we're looking at exactly. Looks like there might be a robot in there.
Yeah, to the left.
Yeah.
Since it's docked, does it have its own solar panel?
No, so there's a...
Takes power from ISS?
Yeah, it takes power from ISS. There's a payload deck called the ELC. I think it's equipment logistics carrier that has comm and power available to different types of setups, experiments. There's actually a whole bunch of places for different experiments on ISS. It's really kind of pretty amazing tool because it makes it a lot easier for people like me that are trying to develop new technologies to get them into space, and you don't have to build your own spacecraft, right, to get into space, because there's one up there and they go up all the time just to bring food and water and stuff, right? So, yeah, there's a whole slew of different facilities.
How long is it contracted?
Raven?
Yeah.
So Raven, the mission lifetime is a year. And let's see, we got up there in February this year. And so we might get extended depending on funding, what's going on with Restore or whatnot. But eventually they'll pop it off and probably discard it, send it to burn up in the atmosphere. But that's just kind of how it rolls. I mean, maybe if we get lucky, they can stick it in the trunk, the Dragon, and we get it back. But that's the plan as far as I know. Anybody got any other questions? Laser related? It doesn't have to be.
Is this one piece that goes up? How do they get this whole piece? How do they get this whole piece? How is it one?
Okay, yeah, so the Golden spacecraft was launched like 18 years ago or something, right? That's been up, that's Landsat 7, been taking pictures of the Earth and running out of fuel, right? The bottom guy is an entire, what that's probably more representation of the payload deck, right? So Goddard is building the payload deck, and that includes the arms, the tools, the sensors, the computers, algorithms for driving the thing, all that, right? And then there's a spacecraft bus, which is thrusters and the tanks and the solar array and kind of the typical things that you need in a normal spacecraft, right? So we actually procured the spacecraft bus, and we will make the payload deck to that bus, and then stick that on a launch vehicle and send that on, right? And so that has everything you need to fly up to a spacecraft like this, or this one specifically, is what we're planning for. Does that make sense? Answer your question? Okay.
Are you guys working with DARPA?
Yeah, DARPA has its own geo-servicing project.
But they're going to start.
I don't know. To be honest, I haven't kept up with that. But from what I understand is they were going to service communication satellites, geosynchronous orbit, and we're focused on the low Earth orbit spacecraft right now. But yeah, we collaborate with those guys all the time. We're at their reviews, they're at our reviews. We do sensor testing together. So we stay real connected with them. All right, well, I think maybe that's all we got. Oh, Peter, you got anything good? How early am I ending? 20 minutes now. All right.
Give us a demonstration.
Yeah, demonstration. Unfortunately, the sensor is in the lab right now.
So is much of this
Like steering the robot? Yeah, they don't let me do that.
much of this derived from the arm?
From ARM? We did a lot of work for ARM, for the astro retrieval mission, but and advanced things there. All this technology was going to be directly usable on ARM, right? So it was another implementation of our technology. Yeah. And we used to have a giant boulder right there for people to look at to get an idea. But it was, I mean, it wasn't a real boulder; it was made out of foam, right? But giant fake asteroid. Yeah, it was, we were going to go and pick up a 70 metric ton boulder off the face of an asteroid, which would have been pretty cool.
Yeah.
But we're not going to do that anymore. Yeah. All right, so we got a smart robot guy to come and talk to you. Since I don't know robots.
Are you gonna stay and do lasers?
This is Brian. No, I'm all tapped out.
He's had enough trauma for one day.
My name is Brian Roberts. I work robotics here at Goddard. Do you have any questions in particular? Robotics. Is that on? What's that? Is that on? Yes, I think so. I'll hold close enough.
So what's that used for?
So what we do is mostly simulate space robots. So if you know anything about space robotics, there's a big arm on the space station. The shuttle had an arm. A couple different various robots are on Mars. Typically, you build space robots to only operate where they need to go. So in space, there's not gravity, so you don't need big, shoulders and elbows and wrists. So the arms are pretty wimpy, which is great for space because it means I can launch a robot to space and launch more food for the astronauts, fuel for the spacecraft. What it means when I'm testing it on the ground, it can't lift the sensor and gravity. So I can have fancy offload systems, but then you subtract out the offload weight. It just gets really tricky. So the tact we've taken is we use these industrial robots that simulate the robots working in space. So you can't actually launch this into space. It doesn't have the right materials. Didn't have all the right quality controls put together because the Japanese and here in the United States produce these things, tens of thousands at a time. These are all over automotive factories. In fact, if you have an IKEA bookcase at home, anyone have one of those? If it was assembled robotically, this is the model robot that's used to assemble. IKEA is using these robots to assemble bookcases. So the cool thing is these are by a couple orders of magnitude less expensive than a space robot. Space robots are in the tens to hundreds of millions of dollars. These robots are in the tens to hundreds of thousands of dollars. But they come in assemble bookcase mode. They don't come in simulate space robot mode. So all the workstations you see here and the folks down the back there spend a lot of time basically tricking these robots to use software to make it seem like the end of the robot there And you can see the end is obviously not a commercial thing, it's an actual engineering unit of the tool drive that goes on the space robot. So the idea is the same software that drives the space robot drives this robot, and all we care about is where the end of the robot is. I really want to get that tool at the end in the right location, and so the same software that drives both robots, I'm getting experience using those algorithms and all that software to try all that out, but I can do it on a much less expensive robot than I can a space robot with all of these fancy offloads. Or you could go to neutral buoyancy, drop things in the water, but then you can't do all the fancy laser stuff that Nat talked about. It doesn't work very well in the water. So we've used these industrial robots to be a stand-in for the flight robot. So if you look to the right, you see that kind of gold robot there. That's what the space robot looks like. What that is a mock-up of the robot they use when they're building the flight robot to make sure all the wires go in the right spot. So it's the same length, it's got all the shoulder and elbow and everything's in the right spot. As you can see, it's much wimpier than the commercial robot here. And if you can peek down the end, it's probably covered up, you can't see it. We've got an engineering version of the flight robot that we built just to make sure before you build the real flight thing, because flight robots are even more expensive, you want to make sure you got all the engineering correct. You tend to build it's like going to the World Series. You don't go straight to the World Series. You play preseason, you go to the playoffs. And during the year, it's the same thing. We built an engineering unit, so that's down there. It looks just like this one, except for it's got motors and it can actually move around. This one is just a kind of static mock-up that we use to show where another robot arm would be to have the true robots working together. So that's what we use these for, is to simulate, in this case, all the servicing tasks that Matt talked about. So the bottom left is the fill and drain valve where the fuel gets put in the satellite. These robots move the tool, so we can debate and argue over, you see the adapter here, the colors here, what color shows up best in the cameras, right? The walls are black, so we can shut the lights out to simulate space, and use the lights on the payload deck and on the robot to illuminate things. So maybe blue shows up better than green. You want to know that before you get to space, so we use this to simulate all that with these robots standing in for the flight robots, and try all that stuff out. How long is the tool? How far do you move? How do you cut the blanket? How do you peel it back? All those sorts of things get tried out on these robots. And then that same software is what's used to put on the flight processor that Nat talked about. That's very similar to what's on Raven, is where the flight robot algorithms go to drive the flight robots. So that's what happens here. What you can see, and I apologize for making a bunch of noise down there, what's happening next door is this arch structure here. We've got the engineering robot that will eventually get mounted up on the arch. It was up there earlier, it's got taken down. And you can see in the middle that 80-20 structure with a platform there. That's to simulate the spacecraft we're going to go grab. So you can see the setup here, as Nat talked about. Landsat is the thing we're servicing. It's kind of set in 3 berthing posts here. You can see 3 kind of silver posts going up. So it's stationary. I touch it, it's not going to move. It's like I've held on to something as I'm working on it. The problem is, as Nat said, these satellites weren't designed to be serviced. So I reach out and grab that thing. When it's floating in space, what's going to happen to it as soon as I touch it? It's going to move away from me, I'm going to move away from it. So that's very challenging. As Nat said, no one's done that before. The Europeans and the Japanese have done kind of what I call friendly rendezvous, where they have, as he said, fiducials or lasers or rangefinders or GPS talking between 2 vehicles. That's much easier. The self-driving car analogy is much easier when you kind of know that ahead of time. Landsat was launched, no one ever anticipated servicing it, so there's nothing on it to tell us what to do. So we want to simulate that grab when I grab the thing and it floats away from me. So what we have is the arm will be on the arch, simulating the silver portion that Nat mentioned, where the arms are mounted, all the rendezvous sensors, all the tools. And what I do is I take the bottom part of Landsat and I put it on that platform. If you come here next week, there's 6 legs that will go down. So when I touch Landsat, it's got a sensor behind that ring, the Marmon ring that Nat mentioned. When I touch that, that force and torque gets fed to the computer. The computer programs the robot to move like it moves in space. So if you're here, a couple months from now, we could program that to have the right properties of Landsat. So when I touch it, the center of gravity is here. I touch it here, it would move and shake. I can also, he mentioned the solar ray on the back. The solar ray is going to start flapping like a bird. All those dynamics are simulated on the robot. So when I reach out and grab it, I'm not going to trick myself that I can grab this fence all day when it's folded down. I get to space, I grab the fence, it moves away, I move away. Oh my goodness, what am I going to do? We've had trouble or challenges at NASA trying to simulate that on flat floors. Well, guess what? There's no flat floor in space. So you train on the ground, flat floor prevents this thing. I go into space, I touch the satellite. Oh my goodness, the flat floor is not preventing the satellite from moving. You want to do a full 6-degree freedom simulation there. So it's kind of that end-to-end to try out the rendezvous, kind of the grapple phase, and then the servicing phase with industrial robots. So before we do all that, it's very challenging. We use these robots, which are much less expensive, to try all the algorithms out. How do you save the system? All that gets tried out in the far end of the room. You can see the mock-up in the back. That actually goes 12, which is one of the early mock-ups we were using on another platform just to work all the software out, and then eventually we tried with engineering.
What TLL?
So the question is, what TLR? So I would say, a lot of the Raven stuff you guys do on the station is, 8, 7, 8 high. The algorithms here are pretty high. They're running on a kind of an x86, right, a PC. So they're not quite mature because they're not running on the right platform. So that's why he mentioned the robotic refueling experiment. A lot of these tools are at the 7, 8 range because they were actually on space station, a different robot, so it's not identical, but demonstrating servicing on a panel like this. So those are much higher. The robot, a lot of the technology in it came from the Mars program. So we've got a company in California that built all the arms on the Mars rovers. If you look at the arm when it's uncovered down there, you'll see a lot of the actual actuators themselves that move the arm around are direct sisters or brothers of the actuators on Mars today. So different environment, Mars versus low Earth orbit. So we've got a range from, some of our stuff is very early, brand new stuff all the way up through 7, 8. And we're trying to mature as much as we can by doing things on station like Raven and RM3 coming up to mature that to make it. And then buy down the risk here by shutting lights out to make it more relevant environment to advance those technologies even more as well.
How many people does it require? How many people do you need to manage this up there? So it all comes out. How many people do you need?
Very good question. So this will be, as Nat mentioned, so we're kind of try things out. During the mission, this will be our, well, you saw the movie Apollo 13, right? When they went and said, we have a problem in orbit, let's go figure out what we're going to do. This is what we're going to do here. If you look upstairs where the windows are, that's going to be our control room. And I think when we're rendezvousing, we've got maybe 40 or so people sitting in the control room watching everything.
How many people?
And actually control the robot, we've got 3. So there's one sits in the front room talking with everyone else, and there's 2 people sit at a workstation like that should control the robot.
None of the astronauts, right?
No, this is not. It's all controlled from the ground. And that's actually one of the challenges. So Nat mentioned the rendezvous phase. This here can all be joystick from the ground because you can move slow and wait. When you're trying to rendezvous, you've got 2 very expensive assets close together. That's all autonomous because the time delay, if you see the screens on there on the wall, that happened in space about a second ago. Just because of the time delay through all the satellites. When we're doing restore, it's about 6 seconds. So if we're trying to joystick that grab, I'm going to grab where the satellite was 6 seconds ago. So the robot has to do all that itself. So that's no people on the ground kind of controlling the robot, but watching, making sure it's doing what it has to do. So anywhere between, like, say, 40 to 50, and a whole back room of, probably another couple dozen people watching. Because it will be, as Nate said, the first time anyone's ever done this.
Yeah.
We've done plenty of rendezvous that were kind of cooperative, friendly, designed for that. This is the first time we've ever done that fully autonomously. So probably a lot more people the first day and the first week, and then we'll tail off as we go through the missions. I think Peter said the next group maybe is ready.
I'm here to give you the hook.
Cool. Perfect.
Thank you so
Thanks
much.
for coming by. Thank you.
Thank you.
Yep.